In today's class, we're going to learn about, we're going to be in chapter 8, which is about mechanical properties of materials. Okay, and what I want you to think about is imagine if you were to go out, say, in my backyard and do a little yard work and pick up a whole bunch of different sticks. So if we're picking up some sticks in the backyard, I sometimes like to do this in class, is just bring in a whole bunch of sticks and say, can we predict which ones I'm going to be able to break? Okay, and if you imagine doing this, let's say I have a little tiny twig, tiny cross section, and I pull on it. Maybe I can break it, maybe I can't. What if it's a giant log? Probably can't break that by pulling on it. Probably nobody can break it by just pulling on it. What if instead of trying to just pull on it, what if I go back to my little twig example and instead I try to bend it? So maybe I grab it with one hand and then I push my knee on it to try to bend it. Probably a lot more likely to break it than just pulling on it. What if it's a big log? Right? We could try to support it on the two ends and then maybe jump on it that direction. Imagine rotating it sideways. Yeah. So it turns out I can always find some branches that are small enough I can break, and I can find some that are big enough that I can't break. And it does make a difference whether I pull on them or bend on them. So I like to kind of use this to introduce the topic of kind of the strength of materials. What is it that actually affects the strength of the material? Right? I just showed you a couple of examples, right? First of all, might be size, right? I just showed you two different sizes, right? A thin twig versus a big log. The big log can support a whole lot more load than the thin twig can. But we didn't even talk about what about material. I have a lot of different trees in my yard. Does it make a difference if it's from a birch tree or an ash tree or a maple tree or a pine tree? They probably have a little bit different material properties than each other. Does it make a difference if the material is dry versus wet? I'll tell you, it makes a big difference. Dry sticks, we recently cut down an ash tree that had died, and I had, logs that were fairly big in diameter, 3, 4, 5 inches in diameter, that actually just snapped off because it was completely dry and diseased and ready to be cut down. So dry versus wet makes a big difference in material. Also, the loads. It makes a big difference whether we're pulling on something versus bending it. Okay, it simply puts the material into a different state of stress. We're going to be talking about stress for the rest of the semester. And that state of stress can be more damaging to the material. All right, so what we want to talk about today is how is it that we can try to take all of this information and boil it down into some fairly simple things we might be able to look up in a table for the different materials that we want to design with. So I want you to think about scientists and engineers. We want to try to simplify things. Loads we can deal with because we've taken statics already. But the size effect, the material effect, we'd like to try to consolidate that into something fairly robust that we can maybe look up in a table. So scientists and engineers design tests in order to quantify material properties. Right? I want to be able to just go look up if I'm making something out of A36 steel versus stainless steel versus titanium or copper. I might want to just be able to plug in some tabulated values that somebody else has calculated who does a material testing lab. The kinds of tests they typically use are things like tension tests. Tension test, you may have seen something like a little dog bone sample before. The idea is you have a part to grip here on each end, and then you pull it in tension, and you measure what happens in that thin down region in the middle of the dog bone. That's not the only kind of test, though. We can also do compression tests, where we usually take a little cylinder of a sample and we put it between two flat plates and we compress it and we measure what happens. We can do shear tests. There are a few different ways to do shear tests, but a really simple one would be to think about taking maybe just a cube of material and putting it between two plates and sliding the plates in opposite directions. And we also can do bending tests. One of the common ones that are used is called 3-point bending, but there's also 4-point bending. 3-point bending, you put it between a couple of rollers or supports and you push down in the middle. 4-point bending, you still put it between two supports, but we do two separate loads a specified distance apart. All right, so we have a lot of different kinds of tests that we might do. Let's talk a little bit about that tensile test. What would happen if I run the tensile test? If I go to run it, so consider that simple test. Consider the simple tensile test. Okay, we're gonna take our dog bone specimen and we have this nice uniform, what's called a gauge length region. That's the part that's really gonna get stretched, right? We're gonna grip it down here and apply a load P. Up here, apply the same load P. And what we're gonna measure, we have some kind of an initial length here of our gauge length section. We're gonna put maybe an extensometer on there between these 2 points that are a little hard to see. Let me change the color. Maybe I have a couple of points here that I might put on and either do this visually with a system that visually measures the displacement of locations, or we could do it using a clipped on extensometer. So what's going to happen is as I pull on this, it's going to stretch. And I'm going to be measuring the force P and how much elongation I get from that middle L0 section. It's going to get a little bit longer and I want to measure that. The other thing that we'll need to know down the road is what is the cross-sectional area here? Okay, so what we're going to measure in this test is P and the change in length. So we're measuring the force and the change in length. And if I do this for a bunch of different samples, P versus delta L, well, maybe one sample looks like this. And then maybe I test another sample that's a different size and it looks like this. And then another sample, it might look like this. And another sample might look down here like this. And can you see what's going to happen if I test things with a lot of different sizes is as the change, if I use different sized specimens, I get a totally different curve. And that would be a pain in the neck to put into a tabulated kind of way for engineers to look up a material property. So we don't want to use force and deflection because the problem is if I use a big sample versus a small sample, I get a totally different force value. So we want to try to see if there's a clever way to normalize force and normalize deflection so that I just get a single curve no matter what size my sample is. So the idea is to remove the effect of size. We want to calculate something else to plot, some other quantities to plot. So that the hope would be that our curve, when we're done, whatever we plot that's kind of like a load versus whatever that's kind of like a deflection will hopefully all lie on the same curve. That's the hope. But I don't know what we're going to plot on the x-axis and the y-axis to get there. So we already figured out that probably how much force it's going to take to deform this depends on how big that cross-sectional area is. So that's where we're going to start. We're going to define a quantity that we call, we've used it before in this class a little bit, called stress. Specifically, it's normal stress, since we're pulling this. And normal stress, we're going to use the Greek lowercase letter sigma, is going to be defined as just P over our original area A naught. This is also sometimes called engineering stress. And I want to remind you that is the Greek, sorry, I should capitalize Greek probably. Greek letter sigma. It's just like a little O with a tail. Okay, and this A naught, that is the original cross-sectional area. So what kind of units will this have? This stress is got to have force units on the top, pounds, and area units on the bottom. So the units will be either PSI or pascals, just as you'll recall is a Newton per square meter. Okay, so that's what we're going to plot on this horizontal or on the vertical axis. This one's going to become sigma in units of, for example, PSI. And then what about that horizontal axis? Well, we tried to plot delta L, but delta L is kind of a problem because if you imagine pulling a really short tensile bar versus a really long tensile bar, they're probably going to stretch a different amount. So we want to take out the effect of length. All right, to remove the length effect, the next quantity we're going to use is called normal strain, also called engineering strain. And it looks like a lowercase Greek letter epsilon, and it's going to be that change in length divided by the original length. Okay, this is the Greek epsilon, and its units are actually dimensionless. Sometimes people will call it inches per inch or millimeters per millimeter, but technically that's dimensionless because those inches cancel and those millimeters cancel. All right, so we have two key equations so far for today: the definition of normal stress and the definition of normal strain. And then we'll put that normal strain on the horizontal axis, and guess what? All of our curves are going to land right on top of each other now, no matter how big those tensile bars are. So let's look at that. We're going to call it a stress strain curve. Let's look at it in a little bit more detail. There's my strain axis, there's my stress axis. What happens with the vast majority of materials is when you start testing them, we have this initial part that is a straight line. Well, because it's a straight line, we're going to calculate the slope, and that slope is going to be another quantity in just a minute. Well, what happens after that is you usually start departing from proportionality just a little bit. You can call that the proportional limit. And then we have a point that's kind of called the elastic limit, i.e. the yield stress. I'm going to put it right here. Yield stress. We're going to use this one a little bit more later in the class. This one right here is the proportional limit. And the idea is that if you were to load up your sample anywhere along this part of the curve before the yield stress, it would unload right back to zero. You can pull it and unpull it, pull it and then let go of it, and it snaps right back to its original shape. So we oftentimes call this part right here the elastic region. Elastic, same word we use for an elastic, like a rubber band, something that can be stretched and unstretched and pulled back and forth over and over and doesn't ever change permanently. If you keep going, keep applying more load past the yield stress, then we get into permanent deformation. And what usually happens is we start to get some strain hardening and then eventually fracture. Although things get a little funny here, it kind of depends on what we plot. But at the end, you're going to have some kind of failure. Usually a strain hardening, but all of this is the plastic deformation region. And for this purposes of this class, we are not going to pay any attention to that. We're assuming that for most engineering design, you want to be able to reuse the part over and over. You do not want to go into that plastic deformation region. So if you want to know more about that, you'll have to take some advanced classes in plasticity that are probably offered by the material science department or advanced classes in the mechanical engineering department also. But the whole idea is that any deformation in this plastic region is permanent. If you let go, it will be deformed permanently. So you don't usually want to design to be in that region. We're going to stay with the elastic region. In fact, we're going to assume for all of our calculations for the rest of the semester that we're in this proportional limit region right here, perfectly straight line, and we're going to use the slope of that line, which we give a letter E. And if we're using a straight line, we can say sigma is simply equal to E epsilon. Not sure why I'm getting some extra dots on here. Yeah, sigma is just E times epsilon. What is E? E is given the name the Young's modulus, also called the elastic modulus. Those are the two most common names. This equation right here that I'm going to put a box around is called Hooke's law. You've seen a Hooke's law before in physics for springs. Well, this is a Hooke's law for materials. The units of that Young's modulus are going to be the same as stress. They're going to be PSI or pascals, depending on whether you're in English units or SI units. So key definitions are those three boxed equations. I'm going to write them down one more time. We have stress, engineering stress, given by a Greek letter sigma, is force over the original cross-sectional area. We have that engineering strain, given by a Greek letter epsilon, is change in length divided by original length. And then we can relate these two guys. Stress is equal to Young's modulus times strain. So those are our three key equations for the day so far. And then we just want to use them in solving some examples. So I want to do a couple of examples here. First example is going to be pretty quick. And then we'll do one that requires a little bit more thinking. Okay, so for this example, we've got a bar of some kind of material. Don't know what the material is. It's just a rectangular prism of the material. It is 5 inches long, and it is subjected to a tensile load of 8,000 pounds. Okay. We're told that the cross-sectional area of this bar is 0.7 square inches. And we are told that under this 8,000 pound load, the change in length is 0.002 inches. And the problem wants us to find Young's modulus. Okay, feels a little backwards. Usually we know the material, we look up Young's modulus, but let's say we've got some new mystery material and we're in a lab and we're able to test it. And we take these measurements, now we can solve for E. So I'm probably at the end of the problem going to need to use Hooke's law, which says that sigma equals E epsilon. Or if we rearrange that, E is equal to sigma divided by epsilon. So we'll use that equation, but first I need to find stress and find strain. So stress. Stress is P over original area, which in this case is 8,000 pounds divided by 0.7 square inches, which if I plug that into my calculator comes out to be 11,428 PSI. And then let's calculate strain. The equation says strain is change in length over original length. I'm told the change in length is 0.002 inches and the original length is 5 inches. Make sure those inches match and that they cancel. And they do, so my strain comes out to be 0.0004. Strains should always be very little numbers, so it's good if you get lots of zeros. So finally, my Young's modulus will be 11,428 psi divided by 0.0004. I should get a big number, and I do. I get 28.6 times 10 to the 6th psi, or we'll oftentimes use ksi because we deal with such big numbers. This is going to be 28.6 times 10 to the 3rd ksi, kips per square inch. So not too bad. 3 equations. They're very simple equations, no calculus involved here, and we're quickly able to get the answer. Let's try a little more complicated example that will allow us to review some statics concepts here. I've got in this problem a beam that is pinned to the wall, and then it's also supported by a cable. Actually, the problem calls it a guy wire. So there's point A, point C, and point B. We are told that this angle is 30 degrees, and the whole thing is 10 feet wide. And I better have a load on here. This is going to be a really boring problem. It has a distributed load, a downward uniform distributed load along the entire 10-foot length of magnitude W, which is unknown in this problem. All right, we are told it is a rigid beam. We're told that the guy wire, AB, is a guy wire made of A36 steel, and it has a diameter of 0.2 inches. So that's our information that we know. Now we're supposed to find the magnitude of the distributed load W that will cause B to displace downward 0.75 inches. Okay, wow, that seems like a lot. I don't know the distributed load. I've never maybe heard of a guy wire before, but it looks like it's a string or a rope or something made of or a wire made of A36 steel. It probably doesn't matter if I don't know what a guy wire is. And I don't seem to have very much information here. So whenever I don't know what to do, I usually just go start drawing free body diagrams and seeing what I can solve for. But I think our solution process ultimately is going to be this. If I can draw a free body diagram and maybe figure out a relationship between that distributed load W and the tension in the wire, right? Can you see that this wire, from A to B is going to be a 2-force member. So it's going to have a force in it that probably pulls up at point B to hold the beam up. But that wire, we're now going to treat it like it's deformable. This isn't statics anymore. Now things can stretch out. So the wire is deformable, and as it stretches out, it's going to allow beam BC to rotate downward about point C, and then B will be able to drop a small amount. So what I think I'd like is an equation that somehow relates this distributed load W to the force in the guy wire. And then I probably need to do a little bit of geometric analysis to figure out, well, how much force would it take in the guy wire to cause it to stretch out enough that this beam would rotate enough for B to go down 3/4 of an inch. So let's take this one step at a time. Let's do the statics part first. I need a free body diagram, and I'm going to do that beam from B to C. So C had a pin, so I'm going to have an unknown CY and an unknown CX at the pin. That distributed load, I'm going to replace by an effective point load whose magnitude will be W times 10 feet because it acts over a 10-foot length. And then finally, my other unknown will be, try to make that sort of a straight line, will be the force in member AB, the tension in the guy wire. I think that's everything on my free body diagram. I wasn't given the weight of the beam to include, so we'll have to leave that off. And now let's see what else we can do from statics. Let's write some equilibrium equations. In fact, I'm going to save us a little bit of time and just write the one equilibrium equation that will help us solve the problem. It turns out I'm not going to ever need to know Cx and Cy. So let's just sum moments about point C. They have to equal 0. And what I was looking for here was a single equation, a relationship between FAB and W. So as far as the moments about C, the vertical component of FAB, that's FAB sine 30, is 10 feet away from point C. That's the perpendicular distance. The horizontal component of FAB is pointed right at point C. It does not cause a moment. And now in the other direction, I've got W times 10 feet. That's the magnitude of the force from the distributed load, and it acts 5 feet away from point C. And that all has to equal 0. If I rearrange this and solve for W, I get that W is equal to FAB sine 30 divided by 5 feet. And I'm going to save that and use it later. Because that's as far as I can get with statics. It's just a relationship between those two. Now let's see if we can figure out the geometry of this problem. So before we have a 10-foot length, we have point A up here, and we have a 30, 60, 90 triangle with 30 degrees right there. Let's just, this is the before picture, before any loads. So using sines and cosines of 30 degrees, the fact that the hypotenuse isn't 10 feet, it's that side that's 10 feet. So I can figure out the hypotenuse and the other side, and they come out to be 11.547 feet, and half of that, which is 5.7735 feet. And you do want to keep a lot, let me clean that up a little bit, it looks kind of bad. You do want to keep a lot of decimal places here because our deflection is in inches and these are in feet. So that deflection is going to be pretty tiny if you don't keep enough. I only wrote down 3 or 4 decimal places here. I think this is actually a 0, would be the next decimal. If you don't keep at least this many decimal places, you will have, the rounding error will cause you big problems. So let's look at the after geometry. So starting with that triangle that we had, what's going to happen is that 10-foot bar is going to rotate downward a small amount. It's still going to be 10 feet, but the important thing is that this downward deflection is 0.75 inches, which I like to convert to feet, 0.0625 feet. All right. So that's the new position. What I want to figure out is, I'm going to do a couple of steps here. First, I'm going to look at this little triangle right here and figure out the little angle in there. I know 2 sides of the triangle, it's a right triangle, so I can figure out that angle. If I do that, what do I get? It's this, the sine of theta, sine of that theta. Let me sneak it right here. Sine theta equals 0.0625 over 10, and those are both feet. And so this little theta, the additional bit that we get there, comes out to be 0.3581 degrees. All right, how am I going to use that? Well, I'm going to use a different triangle that uses this original vertical side, this 10 feet side that I know, and now this is the new position of segment AB, right? Before it was over here, it was 11.574 feet, or right here in this picture. Now point A didn't move, but point B moved downward. So now here's the new AB right there. And I have this purple triangle, which will help me figure out how long the new length is. So I know this original side is still 5.7735. On the vertical side, I've got my 10-foot side. And now this total angle in here, well, it was 90 degrees before the deformation. Now it's going to be 90.3 2.3581 degrees. So it's just a tiny bit bigger than a right angle, which means I can't use sine and cosine now to find that the new length of AB. Should I write the A's and the B's here to remind you guys that's A and B? So this is the original length of AB. And over here is the new A, didn't move, and the new B did move. So we're looking for the new length of AB. I know the side, the angle on the side of that triangle. So law of cosines will work to find the unknown new length of AB. So we'll call it AB new. And law of cosine says that guy squared is equal to 5.7735 squared plus 10 squared. These are all in feet, right? That would be Pythagorean theorem, but we have to correct it. So it's minus 2 times 5.7735 times 10 times the cosine of the angle between them, 90.3581 degrees. Cosine of 90 is 0. So when it's an actual right triangle, you just get Pythagorean theorem here. All right, solve it. And we get that the new length of AB is 11.5782 feet. Again, keeping lots of decimal places here. So now we can find strain, right? We know the old length, we know the new length, so we can find the change in length, and we know the original length, so we can find strain. So strain is going to be delta L over the original length. So I'm going to put the new length, 11.5782, minus the original length of AB, 11.5470, divided by the original length, 11.5470. And you can start to see why if I don't have a lot of decimal places, I'll get a really badly rounded number. This comes out to be 0.0027027. So that is the strain that you have to develop in the guy wire AB in order for B to go down 3/4 of an inch. Now that I know the strain, somebody told me this was made of A36 steel. Okay, here's a table lookup. You flip to the back of the book, and there are 2 tables in the back of our book. One is for US customary units, the other is for SI units. So I want to look at the US customary units. And under steel alloys, it has a listing for structural A36 steel. And in the column for modulus of elasticity, it just says a 29. Well, 29 what? Make sure you go look at the very top of that column. It says modulus of elasticity E in 10 to the 3rd KSI. So I need to write down times 10 to the 3rd KSI. So that's the value I get from the table in the back of the book. So now we can use Hooke's law. Stress is E times strain. So plug in our strain, 29 times 10 to the 3rd KSI times 0.0027027, and we figure out the stress, which I can't find the page where I wrote down the stress. There we go. Stress comes out to be 78.4, and the units are KSI because I had units of KSI right here, so I have units of KSI right there. We are getting really close. I know stress. Once I know stress, I can use the definition of stress to figure out how much force we need in that wire. So stress, the definition is stress is equal to force over original area. And I want to know force, so let's rearrange this. Force is going to be stress times area. So this is 78.4 kips per square inch. And then my area, I believe they gave us a diameter, right? It says the guy wire is a 0.2 inch diameter. So area will be pi radius squared. So diameter, you put in the diameter, 0.2 inches, you divide that by 2 to get radius, and then square that. And if I multiply all of that out correctly, I get 2.462 kips. That's the force that we need in the wire to cause enough stress to cause it to strain enough so that B moves down that 3/4 of an inch. Now, remember that equation I said we'd save for later? That's this equation right here. Let me just copy it and bring it down. So this came from statics, right? And it tells us if we know that force, 2.462 kips, multiply by sine of 30, which is 1/2, and we divide it by 5 feet, we end up getting 0.246, we'll round it to 3 sig figs at this point, kips per foot, which are the right units for a distributed loading. And we have solved the problem. We had to put together a lot of pieces to solve this problem though, right? We had to, at the very beginning, draw a free body diagram and figure out a relationship between the force in the wire and the distributed load. We did that by summing moments about C. Then we needed to use some geometry of the problem to figure out the original length of AB using the sine of 30, or actually cosine of 30 since we knew 10 feet. Then we did a little bit of geometry here to figure out what the new triangle would be once point B had moved down 0.75 inches. That gave us a new length of AB. Then we had to pull, well, using law of cosines, our favorite. Then we pulled out our new material from today. We pulled out the definition of strain, our Hooke's law, and the definition of stress to finally figure out how much force it takes in that wire for it to stretch out enough for B to move down. And then finally we went back to our statics equation, equilibrium equation, to figure out the distributed loading. All right, hopefully you're still with me. We have one more new equation / definition. We'll call it a material property. So we have one more material property for today. It is called Poisson's ratio, or if you like to speak French properly, Poisson's ratio, which is the French word for fish, but this is actually named after a person, not an animal. For Poisson's ratio, we are going to use a Greek letter nu, which kind of looks like a curly V, at least the way I write it. Greek letter nu. Okay, what is it? It's going to be a dimensionless property that is the ratio of minus the ratio of the strain in the lateral direction over the strain in the longitudinal direction. Okay, what in the world is this? The idea here is if you take a piece of material, I'm going to draw it a little bit bigger. Let's say I take a cylinder of material and I pull on it, right? We're going to apply a force P. Well, we all hopefully realize that it's going to stretch out a little bit. Okay, so it's going to end up a little bit longer due to my pulling on it. But something else is actually going to happen. And this is a little hard to visualize unless you're pulling things that are really big and stretchy like elastic bands. But in addition to getting longer, it's actually also going to contract a little bit in the lateral direction. So we refer to this as kind of, the horizontal direction is kind of the longitudinal direction because it's the long length. And we refer to the perpendicular direction as the lateral direction. And so when you pull on something in the longitudinal direction, it gets longer. So epsilon longitudinal, well, that's just delta L over L naught. That's the strain we've been using all day. What is epsilon lateral? Well, that's going to be delta radius over the original radius, or you could write it as delta diameter over original diameter. Or what if it weren't circular? What if this were square? It could be delta width over original width. And why do we have a negative sign there? Well, if we get longer when we pull on it, then epsilon longitudinal will be positive. But that contraction, that would mean the radius is getting, or diameter or width are getting smaller. So epsilon longitudinal is going to be usually positive. And epsilon lateral is usually going to be negative. So negative divided by a positive would be negative. So we add this extra negative sign in the definition so that the actual ratio, which is a material property, is a positive number. Okay. And it turns out that Poisson's ratio is dimensionless, because it's a dimensionless number but divided by a dimensionless number, which is really dimensionless. So nu is dimensionless. And it has to range in value from 0 to 0.5. And is usually around 0.3. For a large number of engineering materials. All right, so let's do one more example and then call it a day. Example 3. I've got a cylinder that is 200 millimeters long, and it is being pulled on by a 300 Newton force on each end. And we are told this is made of some kind of an acrylic. That's the kind of plastic. It's got a diameter of 15 millimeters. And we're told the acrylic has a Young's modulus of 2.7 gigapascals. And there's a Poisson's ratio of 0.4. I said 0.3 is fairly typical. 0.4 is a little more common for polymers and plastics and rubbers and things. Rubbers, it can be even higher, like 0.49. We are asked, though, to find the change in length of this bar and the change in diameter. Okay, not too bad. We don't have to do any statics for this problem because we're already told that it's just a bar being pulled with 300 newtons of force. So I like to usually start with stress, right? If I can use the force divided by area, I can get stress. Then I can use Hooke's law to get longitudinal strain. So let's do that first. Stress. Sigma is force over original area, which will be 300 newtons, divided by pi radius squared. Well, the diameter is 15 millimeters over 2. We square that. And I'm going to get a number. Comes out as 1.697 newtons per square millimeter, which happens to be 1.697 megapascals. So if you convert the millimeters into millimeters squared into meters squared, you get a 10 to the 6th factor in there. And 10 to the 6 newtons per square meter is a megapascal. You want to see it a little more slowly? Let's do that just slightly more slowly. 1.697 newtons per millimeter squared. I need to multiply it by 1,000 millimeters per 1 meter times another 1,000 millimeters per 1 meter. Those 2 millimeters cancel those 2 millimeters, the millimeter squared. And I'm going to get 1.697 times 1,000 times 1,000. So times 10 to the 6th newtons per square meter. That's 1.697 times 10 to the 6th pascals, and 10 to the 6th is mega, which is what we've got right there. Eventually you just memorize that Newton per square millimeter is a megapascal. But you can also do it with just basic units conversion. So we found the stress. Let's try Hooke's law. Sigma is equal to E epsilon. I already know stress and I know E. So my strain is going to be stress divided by E. So I've got 1.697 megapascals divided by 2.7 gigapascals. I don't like having megapascals over gigapascals. So let's write this as 1.697 times 10 to the 6th pascals over 2.7 times 10 to the giga is 10 to the 9th pascals. So now we plug it into the calculator and we get a lovely small number that is, make sure I'm looking at the right example, 6.2876 times 10 to the minus 4th. There's our strain. It should be a small number. It is a small number. No units because the pascals cancel. But it didn't ask for strain, it asked for delta L. So let's use the definition of strain. which says strain is delta L over L naught. So delta L will be that strain, 6.2876 times 10 to the minus fourth, times the original length, which was 200 millimeters. And I'll get that my change in length is 0.126 millimeters. There's one of my answers. Now let's use that new Poisson's ratio thing we just figured out. Poisson's ratio tells us what? Tells us that Poisson's ratio, which is 0.4, is minus the lateral strain over the longitudinal strain. What I just found, this guy is my longitudinal strain because I was using my length, right? It was about how big a stress is along the length, how big a strain is along the length, how big would the length change? Oh, actually, that's not my, I just pointed to the wrong thing. Epsilon longitudinal is up here. That's the actual strain. So let's plug it in and solve for epsilon lateral. So epsilon lateral will be minus 0.4 times epsilon longitudinal, 6.2876 times 10 to the minus fourth, which comes out to be, I wrote it down somewhere, minus 2.515 times 10 to the minus fourth. And then finally, we'll go back to the definition of strain. Epsilon lateral is delta diameter over original diameter, or delta radius over original radius. It'll both work. So my delta diameter is going to be minus 2.515 times 10 to the minus fourth times the original diameter, which I think was 15. It was 15 times 15 millimeters. So this is going to be a tiny number. It is minus 3.77 times 10 to the minus third millimeters, or if you prefer to write it as minus 0.00377 millimeters to see how tiny it is. Either one will work. All right, and that is the end of our notes on material properties, the beginning of chapter 8.